Hello everyone, I'm Zhang Yuzhu. The title of my paper is Single-Channel Speech Enhancement Student under Multi-Channel Speech Enhancement Teacher. I will introduce the following four aspects. The first one to be introduced is background and motivation. The purpose of speech enhancement is to improve the quality and intelligibility of the target signal. Recently, deep learning, which can leverage massive amounts of data and the varying representations of the data, it has made significant progress in noise suppression. The assumptions of the deep learning-based methods are implied in the training data. The deep learning-based speech enhancement method is formalized as a supervised learning problem, which maps the noisy signal to the clean one. In the training phase, both the noisy signal used as input and the clean signal used as a target are required. However, the noisy and the clean signals are difficult to be obtained at once. The conventional method to obtain the noisy and the clean signal pairs is to synthesize the noisy one from the clean signal using the sound propagation model. Figure 1 shows the training phase of conventional deep neural network training method. How to utilize the real noisy signal in speech enhancement. In some papers, a deep neural network was trained to predict a relatively clean signal from a more noisy signal. Other papers proposed to use a deep clustering approach that trains on multi-channel mixtures and learns to project spectrogram beams to source clusters and correlate with various special features. In this paper, we change the perspective of training data generation. We don't synthesize the input noisy signal while generating the target clean signal. Specifically, we train a neural network-based single-channel noise suppression model using multi-channel model output as the training target. The next one will be introduced is proposed method. We train a neural network-based single-channel noise suppression model using multi-channel model output as the training target. It can be seen as a student-teacher learning method that requires only real noisy data. The single-channel student model tries to intimate the effects of the multi-channel model even though it only uses single-channel inputs. Our proposed student-teacher training method overcomes the mismatch between training data and the real application environment. We don't synthesize the input noisy signal, only applies available real noisy data at training time. Figure 2 shows the training phase of our proposed student-teacher training method. For the teacher model, we employ NVIDIA Performer minimizes the power of the noise not arriving from the direction of the target speaker and aims to reduce the noise while ensuring the target speech undistorted in ideal conditions. For the student model, we choose the neural network-based single-channel noise suppression model, which can research the relationship between the input noisy signals and their reference signals. The student model has encoder-decoder structures. The encoder transforms inputs into latent features and then is reconstructed to the original signals by the decoder. The advantages of our proposed method are as following. Firstly, the multi-channel real noisy signals can be treated as several separate single-channel signals and as inputs of the student model. Secondly, the multi-channel real noisy single signals are processed using the teacher model and used as training targets for the student model. Finally, our student model can train a large amount of real noisy speech X, which can be observed in real applications to close the training target X enhancement, which is the output of the teacher model. This is the loss function of our proposed method. The next one will be introduced is experiment setting. The dataset we used in the experiment is TRIMI-3. TRIMI-3 corpus consists of real and simulation data for each of the training, development, and evaluation sets. The real data were recorded in 4 environments: a cafeteria, a moving bus, next to a street, and in a pedestrian area. The simulation data were noisy speech generated by artificially mixing the recording of the real-world background noise with a specialized version of WSG0 utterances. The student models in our experiment are as following. A convolutional recurrent neural network is an encoder-decoder architecture with 2 LSTM layers to model temporal information between the encoder and the decoder. A gated convolutional recurrent network extends the CRNN architecture to perform complex spectral mapping and incorporates gated linear units. Complex spectral mapping with attention-based convolutional recurrent neural networks (CARN) combines CRNN with an attention mechanism. The evaluate metrics of our proposed method are STOI, PASC, and WER. The last one will be introduced as the results and conclusions. Figure 3 shows the STOI and the comparison of different noise types. Table 1 shows the past results are on the test set of mismatched speakers for 4 scene noise types. In Table 2, STOI results are shown on the test set of mismatched speakers for 4 scene noise types. Figure 3. Table 3 presents the past scores of student models over 6 channels on untrained string noise type. Table 4 shows the STOI scores of using different student model over 6 different channels. Table 5 lists the WERs of the development set and test set when using our approach and the clean target training method as the front-end enhancement model of the ASR. Table 6 summarizes the WERs of our proposed student model, which is trained by all real data in the training set. Table 7 shows the WERs for both the real and the simulated development set and the test set. The student model is trained by all simulation and real data. In this paper, firstly, we propose the student-teacher training method for multi-channel and single-channel. which is effective for single-channel noise suppression with only real noisy signals. We find that it can effectively improve the performance of single-channel speech enhancement and achieve competitive performance compared to the methods using clean signals and a target on ASR task. Secondly, extensive experiments are provided to show the effectiveness of our proposed approach for different challenging test conditions. On the single-channel noise suppression, the student-teacher approach can achieve a better generalization comparability on the mismatched speakers and the different noise types. On the ASR task, the performance of our approach outperforms the conventional clean target training method and is close to a multi-channel teacher model. Finally, our approach provides a new sort of data augmentation. We can make full use of real noisy data to improve the performance of single-channel speech enhancement. This is my all presentation. Thank you for your attention.